Well friends, so far we have discussed the propagation of electromagnetic waves in plasmas. Well, last time we were discussing a very special kind of wave phenomena, the WKV solution to wave propagation in inhomogeneous plasmas, and we considered the propagation of wave in the direction of density gradient. When we were considering the propagation of waves at oblique angle to density gradient, we came across a situation where the wave turns around and there is a possibility of generation of plasma waves. So, before I take over to the discussion of wave propagation at oblique angles to density gradient, I think it is necessary that we understand the character of electrostatic waves. So, today I am going to start rather a new subject, that is the propagation of electrostatic waves in plasmas. In this we will discuss how to express an electric field in terms of a potential, then how to linearize the fluid equations, the equation of motion and equation of continuity, and deduce expressions for electron and ion susceptibilities, and then to discuss specific cases of Langmuir waves and ion acoustic waves which exist in unmagnetized plasmas as well as in magnetized plasmas also. So, today our presentation will focus on waves in unmagnetized plasmas. Well, I would like to refer to 3 books. One is Electromagnetic Theory for Telecommunications, written by Professor C.S. Liu and myself, published by Foundation Books, Cambridge University Press. Second is Introduction to Plasma Physics by F.F. Chen, published by Plenum Press. And third one is Interaction of Electromagnetic Waves with Electron Beams in Plasmas by Professor C.S. Liu and myself, published by World Scientific. Well, as I mentioned that in order to satisfy the Maxwell's equations for plane wave solutions, it was necessary that either you satisfy epsilon effective equal to 0 condition, or k should be perpendicular to E, or k dot E equal to 0. The second is the case when electric field is perpendicular to k vector of the wave, is called EM wave, electromagnetic wave, and we have discussed this case. Second possibility is that plane wave solution can satisfy Maxwell's equations when epsilon effective is 0, and in this case the waves are known as electrostatic waves. For these waves, please understand one thing, that according to fourth Maxwell equation, curl of H is equal to minus I omega epsilon effective E into epsilon 0, of course. So, if right hand side is 0, then curl of H is also 0, and according to second Maxwell's equation, curl of B is also 0, a dot of divergence of H is also 0. When curl of a vector is 0 and divergence also 0, then the vector must vanish. Well, we had also seen this explicitly last time, that H is 0 for these waves. So, these are purely electric waves and we call them as electrostatic waves. Now, before I move further, I would like to examine the third Maxwell equation, which is curl of E is equal to minus delta B by delta T. If there is no magnetic field associated with the wave, then delta B by delta T is 0 and curl of E is 0. Any vector whose curl is 0 is expressible in terms of a gradient of a scalar quantity. I express this E then as minus gradient of a function phi, which may depend on position and time. In general, So, an electrostatic wave electric field is expressible in terms of a potential phi, which in general depends on position and time. I would like to understand in terms of phi what is the wave equation governing phi, and in terms of phi what is the response of electrons and ions to this potential. First of all, a word about the Maxwell's equations. There are 4 Maxwell's equations. Second Maxwell equation I had already written, divergence of H is 0. So, when H is 0, this equation is not meaningful. Third equation is this equation. So, if H is 0, then curl of E is 0. So, when I express E in terms of phi, this equation is automatically satisfied. How about the first Maxwell equation? When you use this E in the first Maxwell equation, which is divergence of D is equal to rho, and for plasmas we write D as epsilon 0 into epsilon effective. Sorry, this is not true. I made a mistake. Let me delete this. For plasmas, D is equal to epsilon 0 into E, simple product of free space permittivity and electric field, because polarization we ignore. So, if I write E as grad phi, this equation becomes epsilon 0 outside del square phi is equal to minus rho, and rho is expressible in terms of electron and ion densities. Thus, this is the equation that governs the variation of potential in terms of electron and ion densities, and if we can express electron and ion densities in terms of phi, then this becomes the wave equation. So, as far as the electrostatic waves are concerned, this is equivalent of a wave equation. Let me write this in terms of electron and ion densities. Initially, the electron density in the plasma is n0 and ion density also is n0. However, when a wave travels, these densities are modified. Suppose this becomes n1 and this becomes n1I. In that case, the Poisson equation or first Maxwell equation becomes del square phi is equal to minus 1 upon epsilon 0 into charge density. Electron density, if I multiply by the electron charge, which is minus E, and ion density by ion charge, which is minus E, then it becomes ion charge is n1I into E minus n1 into E, because the n0 and n0 terms here will cancel each other. So, take minus E out, you can write this as E upon epsilon 0 into n1 minus n1I. This is the wave equation for electrostatic waves in a plasma. If we could write n1 and n1I in terms of phi. Well, this Poisson equation we will use little later. Let us go over to the fluid equations which govern the response of electrons to phi, but a word about the character of these waves probably will be in order at this stage. We are talking of waves going in some direction, which I call as the direction of propagation k, because the electric field of these waves in the direction of k, at any instant if you look, then the field of these waves will appear like somewhere in this direction, somewhere in this direction, somewhere in this direction, somewhere in this direction at a given instant of time. And then these arrows will move in the forward direction with time, with the phase velocity of the wave. What is the consequence of these fields having opposite directions in different positions? That, for instance, the electrons, they will experience a force opposite to the electric field, they will move in this direction, whereas the electrons which are here, they will move in this direction. So, in this region, the electrons are moving away from each other and there will be a decrease in electron density. In this region, there will be a build up of electron density. So, what you would expect is that in course of wave propagation, charges accumulate in these regions. They are accumulated there, they are accumulating there, they are accumulating there, and there is a rarefaction there. So, with the propagation of electrostatic wave, you are going to expect electron density oscillations, and electron density oscillations are connected to velocity through the Poisson through the equation of continuity, and hence let us write down the equations of motion. Equation of momentum balance or equation of motion, that is normally called, is written as m delta v by delta t plus v dot del v is equal to the electric force, which I write as minus E. I will ignore the presence of DC magnetic field, and there is no magnetic field associated with the wave. So, I will not write the magnetic force, but then there is a collisional force. For the sake of simplicity, for the moment I may ignore the collisions also. Then there is a term called pressure gradient force, which is minus 1 upon n gradient of nt. This is the equation of motion for electrons of charge minus E, mass m, density n, and temperature T. I can write Te, electron temperature Te. So, equation of momentum balance involves density, and the equation for density is the equation of continuity delta n by delta T plus divergence of Nv is equal to 0. These two equations are nonlinear. Why? Because in this equation I can treat E as the source and V as the response and N also as the response. So, whenever there is an electric field produced by a wave in the medium, the electrons will respond to the field and they are called the response. The velocity is the effect, E is the cause. Similarly, I can treat density also as variation in density also as the effect caused by this electric field. If electric field of the wave is small, then response will also be weak, and product of two perturbed quantities or weak quantities I can ignore. This process is called linearization. So, in order to solve a nonlinear set of equations, the first step is to linearize them. Linearization means neglect the terms which are of first order. Even prior to that, let us find out what is the equilibrium values of various quantities in these equations. These equations govern the density and drift velocity, average velocity of electrons. In equilibrium, when there was no electrostatic wave in the system, obviously I was not expecting any drift velocity. So, in equilibrium, V is 0 and the density of electrons was n0 and ion density was also n0, because the plasma was electrically neutral. And how about temperature? If the electric field is of very small amplitude, then it does not cause significant heating. So, electron temperature also remains constant. So, first, whenever you have to solve a set of nonlinearly coupled differential equations or partial differential equations, you must always start with the equilibrium. It is a general technique employed for electromagnetic waves as well as electrostatic waves. So, first of all, let me write down the equilibrium. In equilibrium, my density of electrons is equal to n0 and drift velocity of electrons is 0 and temperature just a constant, so I do not bother about it. Then I perturb the system, there is no electric field. Now I perturb this equilibrium, so let me write the perturbation. I am writing my electric field E is equal to minus grad phi, and I am treating this E to be a perturbed quantity, and phi, well, I will explicitly write phi in terms of position and time little later, but then when the electric field of the wave is there in the system, density I would expect to become n0 plus some change called n1. And how about the drift velocity? The drift velocity was 0 in the beginning, there is some value given it acquires because of the wave called V1. But I will treat this phi, n1 and V1 all small quantities, and in the process of linearization of those equations of motion and continuity, I will ignore the product of these quantities. So, let me first write down the linearized equations of motion and continuity. So, linearized equation of motion. This equation is m delta V1 by delta t plus V1 dot del V1, just substituting for V equal to V1 in the equation of motion. Right hand side is E grad phi, this is the electric field, electric force. Then there is a pressure term which is, I take constant temperature, so T comes out of this upon n0 plus n1 gradient of n1, because gradient of n0 is 0. This is the equation of motion. Now, by linearization, what do I mean? I am going to ignore the product of perturbed quantities. V1 is a perturbed velocity, so the product of two perturbed quantities will be ignored. So, I take this term to be 0. Now, as far as this term is concerned, n1 is the perturbation and n0 is the original value of density. So, n1 is very small and n0 is large. If I carry out a binomial expansion of this factor, n1 term will go up and product of n1 with n1 will be ignored. So, rather than going through that step, I just ignore this here. So, this term is nearly 0, because this is already perturbed quantity is there. So, with the neglect of this term and this term, this equation becomes a linear equation or linearized equation, which I can write down as delta V1 by delta t is equal to divided by m E upon m grad phi minus T E upon m upon n0 into gradient of n1. This is the equation of motion after linearization. Similarly, the equation of continuity. The equation of continuity is delta n1 by delta t, because n0 delta n0 by delta t is 0, plus divergence of n0 plus n1 into v1, the velocity nv is equal to 0, but this n1 is a perturbed quantity, this v1 is a perturbed quantity, so I will ignore the product, and hence this equation becomes delta n1 by delta t plus divergence of n0 v1 is equal to 0. This is the linearized equation of continuity. In order to solve these equations, I presume a solution to the Poisson's equation or the potential as A exponential minus I omega t minus k dot r. A wave traveling in the k direction with frequency omega, suppose that it has a potential of this form. Potential is a scalar quantity, so A is also a scalar quantity. Now phi is the source and n1 and v1 are the responses, so I expect n1 and v1 also to vary with time and position as exponential minus I omega t minus k dot r, and this helps us a great deal because wherever delta delta t occurs, I can replace by minus I omega. So then after linearization, replace delta delta t operating over perturbed quantity as minus I omega and del operator by I k. This is time operator and this is space operator. So then these equations, the equation of motion and continuity, with this substitution of these operators in terms of algebraic quantities, they become algebraic equations, and let me write them. Quickly you will see that the equation of motion becomes delta v by delta t is minus I omega into v1 is equal to E upon m grad phi, grad is I k vector, phi minus, there is a pressure term which is T e upon m, which I call as V thermal square, thermal velocity square, upon n0, gradient of n1, grad I write as I k into density perturbation, and the equation of continuity becomes minus I omega into n1 plus divergence of n0 v1, divergence del operator is I k dot v1 into n0 is equal to 0. This equation straight away gives n1 is equal to n0 k dot v1 upon omega, and this equation gives me v1 is equal to two terms, one is minus E k upon m omega into phi, the other one is a plus term k vector V thermal square, thermal velocity of electrons square upon n0 into omega into n1. So from the above equation, if I write down the value of n1 in terms of v1, I can, or rather from the lower equation I use the value of v1, I can write down n1 in terms of phi, because in order to solve the Poisson equation or Maxwell's equation, I need the density perturbation. So N1 is, that is what I require, and I will write down using these two equations N1 in terms of phi, and that turns out to be, I just simplify these two equations and write the solution. So you obtain N1 is equal to minus E k square phi, there is N0 also here, N0 into E k square phi upon m omega square minus k square V thermal square, thermal velocity of electrons square, where I have written V thermal is equal to Te upon m under root. Here please remember, minus E is the electron charge, N0 is the equilibrium value of electron density, K is the propagation constant of the wave, m is the mass of the electron, V thermal is the thermal velocity of electrons. This N1 will be out of phase by pi with respect to phi if this term is smaller than omega square. On the other hand, if kV thermal is bigger than omega square, I can ignore this term and response becomes very simple. In the particular case, for kV thermal much bigger than omega, for low frequency response, this is positive, and this reduces to simply, let me write this, for low frequencies you get N1 is equal to N0 E phi, k square will cancel out, and upon T. This is called adiabatic response. And you may recall this omega square terms comes from delta V by delta T in the equation of motion called inertia term, and this comes because of the pressure term. So at low frequencies, or when omega by k, the phase velocity of the wave is less than thermal velocity of electrons, in that case the electrons respond almost instantaneously to the field of the electrostatic wave. This is called Boltzmann distribution. They all obey some sort of a Boltzmann distribution, or the response is called adiabatic response. Quickly, where the potential is large, electrons will move there, and so on. So this is the, so N1 is bigger where phi is bigger, the same phase, they oscillate. But this is a case, waves that satisfy this condition are called sound waves or ionacoustic wave. But today I will begin my discussion with the high frequency wave for which omega is bigger than kV thermal. That wave is called Langmuir wave, and for that high frequency wave you may note that if I write down a similar expression for ion density perturbation, let me write down that expression, I think then you will appreciate it better. So for ions, the density perturbation for ions would be N1I would be equal to N0 charge of the ion, which I am taking to be singly ionized, into k square phi upon mass of the ion into omega square minus k square thermal velocity of ions square. But thermal velocity of ions is very small as compared to electron thermal velocity. So this term is usually very small and you can ignore this. So I can approximate this as N0 E k square phi upon mi omega square. So for a high frequency wave where Ne, N1 of the electrons is equal to n0 minus n0 e k square phi upon m omega square minus k square v thermal square, because I am choosing this term to be less than omega square. So, numerators of both these terms are equal in magnitude. This denominator is small as compared to this denominator because of the mass, and ion mass is very heavy. So, this term is very large as compared to this term. So, for high frequency waves, for omega bigger than kV thermal, we have n1 much bigger than ion density perturbation, and hence I can ignore the ion motion. So, the high frequency waves satisfying this condition, for those waves I can completely ignore the ion density perturbation, and electron density perturbation is expressed in terms of phi. Well, people like to write down this n1 in terms of a quantity called susceptibility. So, rather than before proceeding further, I can write this in a slightly different way. Density perturbation, you know, I can talk of a polarization. Polarization normally is a quantity that is employed in dielectrics. What does this mean? This is called dipole moment per unit volume. Per unit volume. And what is a dipole moment? Suppose I have a pair of charges, one placed here, the other one placed there. The charge is suppose minus q here and plus q there. The position coordinate of this in a coordinate system, suppose this coordinate is r1 and the coordinate of this point is r2. So, in a system, if I have two charges minus q and q placed at a distance at positions r1 and r2, then the distance between them is called d, which is equal to r2 minus r1, and you define the dipole moment of this pair of charges p is equal to magnitude of these either of the two charges q multiplied by the distance d, starting from the negative charge to positive charge. This is the definition of dipole moment, which I can also write down simply as product of charge and position coordinate. This is minus q r1 plus q r2. If you write down this way, this also the same thing, because r2 minus r1 is d. So, this is the same way of writing dipole moment of an atom. If there are many such particles, you just multiply the position coordinate of each particle with the charge of the particle and add, then this quantity is called dipole moment per unit volume. Now, in case of plasmas, we are talking about charges per unit volume with density n or ni. So, what I should have? So, polarization P in plasmas is defined as electron charge is n e for instance, and minus e is the electron charge. So, this is the density of electrons into charge of each electron. So, this is the charge density per unit volume multiplied by the position of the particle. Now, position of the electrons, they are distributed all over. So, I should really consider, because this is I have to let me call this R e of the electron position, and there should be ion position also, because ions are located with density n0, charge plus E, and ion position is say R I. What should I do? because Ne is equal to N0 plus N1, this is the electron density. So, N0 term will cancel out because ions and electrons are really located at the same place, or Re I can write down volume element position is equal to initial position where ions were located, apply some displacement. So, just put this displacement equal to d, this becomes P is equal to minus N1 E well actually this is R N0 E into D, plus there will be a term which is a product of two small quantities, I can ignore that. Well, this is the way one can proceed. And what is the displacement? This is related to velocity. D dt of displacement is equal to velocity. If you work out from there, you can find a connection between this dipole moment and density perturbation or velocity perturbation. Well, I just want to write this, I do not want to give you a mathematical derivation, I just want to say that one can easily show that the density perturbation that I get N1, which I obtained as minus N0 E k square phi upon m into omega square minus k square V thermal square. If I multiply this equation by E up and E down and epsilon 0 up and down, then this can be written as, so you multiply E here and divide by E here, multiply by epsilon 0 here and multiply by epsilon 0 there. Then you know that N0 E square by m epsilon 0 is omega p square upon omega square minus k square V thermal square into phi. The remaining term is k square epsilon 0 divided by E. This quantity, which is coefficient of phi in this first term, is called electron susceptibility. As we will see that this is dimensionless quantity and susceptibility is also dimensionless quantity. So, we have taken care of this extra factor. If I write explicitly, so people write this is equal to chi E into k square epsilon 0 by E into phi, and the susceptibility I have written as minus omega p square upon omega square minus k square V thermal square. One can show that the polarization P, that the way I was driving in the last page, is equal to epsilon 0 into chi E into E. That is why this constant, independent of time and position, etc., this depends only on electron density in the equilibrium, electron temperature in equilibrium, and omega and k of the wave. This quantity is a characteristic of a plasma, depends on its density and temperature and on wave parameters omega and k. Similarly, I can write down the density perturbation of ions if it is required. In the present case of high frequency wave, when omega is much bigger than k V thermal, you do not require that. So, if I know the density perturbation, I can go to the wave equation. This quantity is known as electron susceptibility. And my wave equation would be, or the Poisson equation would be, del square phi is equal to E upon epsilon 0 into N1. This was my Poisson equation. If I ignore the ion density perturbation, del square again I will replace by minus k square. So, this becomes phi is equal to minus E upon epsilon 0 into k square N1, and put the value of N1 in terms of chi. This becomes minus chi E into phi. You may see the reasoning here that this is the same factor with N1 that was in the expression for N1 in the reverse way. So, that this cancels out, and that if I want a non-trivial solution, then phi will cancel out on both sides, and 1 should be equal to this, or the dispersion relation becomes 1 plus chi E is equal to 0. If you put the value of chi E, this gives 1 minus omega p square upon omega square minus k square V thermal square is equal to 0. You can simplify this and you get the dispersion relation for the Langmuir wave or plasma wave, and that is omega square is equal to omega p square plus k square V thermal square. If I plot this, plot k here and omega there is a frequency omega p. The value of omega cannot be less than omega p because this is a positive term, and the dispersion relation goes like this. So, omega increases with k, the minimum value omega can take is omega p. So, these high frequency waves can have frequencies only bigger than omega p. So, this is one branch of electrostatic waves where ion motion is ignored. If you had included the ion motion, if ion motion is included, what do I get? Well, as I mentioned, ion motion will be important only when the electron response is such that omega is less than kV thermal. So, that the electron term is strongly suppressed as compared to ion term. Only when this happens, and in this case what happens? The ion response turns out to be minus k square E upon epsilon 0 ion susceptibility into phi, and ion susceptibility is written as minus omega pi square upon omega square. You do not have to include the ion thermal effects because the ion thermal velocity is very small because of the mass coming in this denominator. So, if I know this is N1I rather is N1I. So, if I know the electron and ion density perturbations, then the Poisson equation becomes del square phi is equal to E upon epsilon 0 N1 minus N1 of ions. Put these, replaced by minus k square, this becomes phi is equal to E upon k square epsilon 0 with a negative sign, and this becomes k square epsilon 0 by E into chi E into phi, and this also becomes plus then because 1 minus is there, 1 is in this, becomes k square epsilon 0 beta E chi I into phi. All this will cancel out and the dispersion relation is 1 plus chi E plus chi I is equal to 0. If I put these values, it becomes 1 plus omega p square upon omega a square minus k square V thermal square of electrons minus omega p I square. This is minus here, I am sorry, this is minus sign, upon omega a square is equal to 0. But as I mentioned, this term is very huge as compared to this term, unless this is negligible as compared to this. So I ignore this. So suppress this term as compared to this one. When this is comparable to this term, the wave is called Langmuir wave, that I have already discussed. So only when this is less than this ion term is important, and in that case this equation gives you omega square is equal to omega pi square upon 1 plus omega p square upon k square V thermal square. But you know omega p square upon k square V thermal square is the same thing as n 0 E square upon m epsilon 0. This is for omega p square, k square is there, and V thermal square is T E upon m. What you can do, m will cancel with this m. You can write this as same thing, E square upon mi epsilon 0 into mi upon k square Te, because mi will cancel with this mi, so they are equal, exactly same. This quantity I call as ion plasma frequency square, k square is there, Te upon mi, the ratio of electron temperature to ion mass. This quantity is denoted as Cs square. So Cs is equal to Te upon mi. This is known as the sound speed, but we shall learn about it, why this is called sound speed. I am just defining a constant at the moment, Te upon mi under root as Cs. So if I use this omega p square by k square V thermal square as this quantity, then omega square, this dispersion relation for the ion acoustic wave can be written as, you can rewrite this slightly in a different way, omega is equal to square is equal to k square Cs square upon 1 plus k square Cs square upon omega square. For kcs less than omega, you can ignore this second term in the denominator, and so for kcs much less than omega, this omega is nearly equal to kcs. This is the linear relationship between omega and k, and the phase velocity is omega by k equal to cs, sound velocity. So this is the wave whose phase velocity at low frequencies, this is wrong, I am sorry, I made a mistake, it's omega pi square, and it's omega pi. So when kcs is much less than omega pi, the frequency of the wave is like kcs and phase velocity is like cs. But when kcs is large, so as kcs becomes bigger than omega pi, omega approaches equal to omega pi, ion plasma frequency. So let me plot a graph here. I am plotting k here and omega there, and ion plasma frequency is here. Please remember, ion plasma frequency is very small as compared to electron plasma frequency. So these waves always have a frequency less than omega pi. The dispersion relation goes like this. And electron plasma wave was, omega p was much higher here. The dispersion relation was like this. So, this branch is lower branch is called ion acoustic wave, and this is called Langmuir wave. There is a big forbidden gap between omega pi and omega p, the ion plasma frequency and electron plasma frequency. There is no electrostatic wave possible. This is a very important consequence of ignoring thermal motions. Ion acoustic wave will not exist if there is no thermal motion, because the electron response will always be more dominant than the ion response. So, thermal motion is mandatory for the ion acoustic wave. As far as the Langmuir wave is concerned, if thermal motion is not there, then omega is always equal to omega p. There is no k dependence. So, k dependence on omega of Langmuir wave arises because of temperature. So, temperature provides k dependence to Langmuir wave, and it also makes the existence of ion acoustic wave possible. Now, let me mention a few words about the energy carried by these waves. In my next lecture, I will deduce an expression for energy density, but today I will presume it. You know, for electromagnetic waves, we know power flow of EM waves is given by Poynting vector. S is equal to E cross H. For electrostatic waves, there is no magnetic field, H is not there. So, this kind of Poynting vector does not exist. Does it mean that the waves do not carry any energy or momentum? This is not true. After all, this S is equal to E cross H was deduced from Maxwell's equations. How do you deduce this? You write down J is equal to, from fourth Maxwell equation, is equal to curl of H minus delta D by delta T, and then you dot this equation with E, J dot E, and you will get E dot curl of H minus E dot delta D by delta T. And then you interpret this as the energy absorbed by electrons or by charged particles per unit volume, and then you write this curl of this E dot curl of H in terms of a quantity called, this becomes divergence of S, and then there is a term which gives you like delta delta T, actually this minus here, and delta delta T of half epsilon E square plus half mu H square. This is the way you interpret this, saying that this is the Poynting flux, the amount of energy flowing per unit area per unit time. This is how you do it. The entire fallacy is in the interpretation of J dot E. We have seen that in a collisionless plasma, J equal to sigma E, but sigma is imaginary. Then this quantity does not represent a power dissipation. So, it depends on the interpretation of this quantity. If we ignore the interpretation of this quantity properly, proper interpretation, if you ignore, then you get a fallacy, a wrong result. So, the waves which do not have a magnetic field, by a proper interpretation of J dot E term, you should be able to see that the energy contained in the electric field is not half epsilon E square. For an electrostatic wave, H is 0, so this term does not exist. But this is a wrong definition. Rather, in general, in a dispersive medium where permittivity depends on frequency, in that medium the energy contained in the electric field is denoted as WE is equal to half epsilon 0 into delta delta omega of omega epsilon effective into E square, rather than calling this half epsilon 0 into epsilon effective E square. This is the right definition, and when you use this, we shall derive this expression next time, then we will see that the energy contained with the wave is this quantity and energy propagating in the wave is WE into Vg. This is the equivalent Poynting flux for an electrostatic wave, and group velocity is delta omega by delta k, magnitude wise, vector wise, like this. Now, we have seen that for a plasma wave, omega square is equal to omega p square plus k square V thermal square. So, if I want to obtain the group velocity, how much that would be? You differentiate this back to k. So, you will get twice omega delta omega by delta k is equal to twice k V thermal square. So, this is the group velocity. So, you get group velocity is equal to V thermal square upon omega by k, which is the phase velocity. K you can obtain from this relation and write this there. So, group velocity will vanish if V thermal is not there. So, it is the thermal motion which gives rise to finite energy propagation or finite group velocity. If this is not there, the Poynting flux will be 0. So, thermal motions play a very important role in energy transfer with plasma waves. Plasma waves carry energy as well as momentum. Each quantum of plasma wave is called plasmon with energy h cross omega and momentum h cross k. It is called plasmon. The beauty of these waves is, in a thermalized plasma like this, their dispersion relation is like this. K can be very close to 0 or it could be finite. If it is very close to 0, the phase velocity will be very large. They can have phase velocity close to c or close to a few times thermal velocity. But when they become very close to thermal velocity, when the phase velocity becomes very close to thermal velocity, a very important phenomenon occurs, and that is called the phenomenon of Landau damping, that we can discuss on the basis of kinetic theory. But prior to discussing that, I would like to discuss the phenomenon of true stream instability, because that will give you an insight into the Landau damping, but that is a different matter. For today, it will suffice to say that a plasma wave is strongly influenced by the thermal motion of electrons. They provide it a group velocity. These waves can have phase velocity close to c, and these waves can trap electrons and accelerate them to velocities close to c, and this is the basic mechanism of laser based electron acceleration. I think I would like to stop here for today, and then we will discuss other issues in next lecture. Thank you.